Chapter 7 is about chemical bonding and molecular geometry. We're going to take some of the concepts we learned in Chapter 6, such as writing electron configurations, in order to understand why certain different types of elements undergo different types of bonding. Once we learn some basic concepts about chemical bonding, we can talk about drawing Lewis structures and how to determine different shapes of molecules, their bond angles, and what types of polarities the compounds will have. We'll begin our discussion talking about chemical bonds. Chemical bonds are attractive forces that hold atoms together in complex substances. Changes in these bonding forces are the underlying basis for chemical reactivity. One of our goals is going to be understanding different types of reactivity. There are two major classes of bonds. The first is covalent bonding. Covalent bonding occurs in molecules. If you recall, molecules are formed when we have two or more nonmetals together in some fixed ratio by mass. The two nonmetals are sharing their electrons in a covalent bond. The second type is ionic bonding. Ionic bonds form from the combination of a metal with a nonmetal. Typically, compounds that have ionic bonding are solids because ionic bonds are so strong. And when we have an ionic bond, the electrons are not shared like they are in a covalent bond. Instead, they're transferred from one atom to another atom. One of our goals will be to gain some insight into the reason that certain combinations of atoms prefer electron transfers in the formation of ions, which will lead to ionic bonding, while other combinations will undergo electron sharing, which will lead to covalent bonding. When many atoms react, they follow something known as the octet rule. The octet rule says that atoms will tend to gain, lose, or share electrons until they have achieved an outer valence shell containing an octet of 8 electrons. If you have 8 electrons in your outer shell, that would mean that you have a completely full valence shell, and this is very stable. Having a full valence shell with 8 electrons means that the element would match that of a noble gas. This is why noble gases are particularly stable and they don't tend to react, because they already have an octet or 8 electrons in their outer shell. Usually 8 electrons come from having a completely full S subshell and a completely full P subshell. If we imagine we were in the second period, we would have a 2S subshell and we would have a 2p subshell. In our 2s subshell, we could hold a maximum of 2 electrons. In our 2p subshell, we could hold a maximum of 6 electrons. If we add up the electrons, we would have a total of 8 electrons that are in the second shell. And for this rule, we're mostly talking about our main group or our representative elements, because sometimes the transition metals do not obey the octet rule as well as metals and nonmetals from our main group elements. When we start discussing bonding, it's very useful to be able to keep track of valence electrons. Lewis symbols are used as a bookkeeping method in order to track our electrons. What we will do is we will write the chemical symbol surrounded by dots for the number of valence electrons in that particular atom. Let's look at the Lewis symbols for some of our main group elements. In group 1A, the number of valence electrons in any atom in that group is 1. The electron configuration would be NS1, where N represents the shell number. For hydrogen, we have 1 electron that we would put next to its symbol to represent that 1 valence electron. Same thing for lithium, 1 electron and 1 valence electron for sodium. This would continue all the way down the family. For group 2A, all elements in group 2A have 2 valence electrons, so we write the symbol surrounded by 2 dots. Each dot represents a valence electron. Their electron configuration follows the form of NS2. Beryllium has 2 valence electrons. Magnesium has 2 valence electrons. And notice we don't pair up the valence electrons. We write them around all 4 sides of our element tile first before we pair any of them up. Group 3A follows the electron configuration NS2 and P1. Everyone in group 3A has 3 valence electrons, so its Lewis symbol is going to be its element symbol surrounded by 3 dots to represent those 3 valence electrons. Boron has 3 valence electrons. Aluminum has 3 valence electrons. In group 4A, all the elements are going to have 4 valence electrons. Their general electron configuration is ns2 and p2. For carbon, we have 4 dots surrounding our C, representing the 4 valence electrons. None of them paired up yet. Silicone also has 4 valence electrons. Continuing looking at our periodic table in group 5A through group 8A, we can see that in group 5A, all elements will have 5 valence electrons. Their general electron configuration is ns2 and p3. And for nitrogen, that means we have 1, 2, 3, 4, 5 valence electrons. And notice now we had to pair up 2 of them on one side because we had exceeded 4. Same thing for phosphorus. We have 1, 2, 3, 4, 5 valence electrons in phosphorus. All elements in group 6A will have 6 valence electrons. Their general electron configuration is ns2 and p4. So oxygen and sulfur both will have 6 valence electrons. Group 7A is going to have 7 valence electrons. The electron configuration will be ns2 and p5. So all our halogens, fluorine, chlorine, bromine, iodine, are all going to have 7 valence electrons. And everyone in group 8A, the general configuration is going to be ns2 and p6. Recall that group 8A is our noble gases. They have a completely full octet with 8 electrons surrounding each one of them. So we have 2, 4, 6, 8. You can always look at the group number on the periodic table for the representative elements in order to tell you what the number of valence electrons is. Most of the compounds we encounter in our everyday life are molecules. Molecules are made up of 2 or more nonmetals together and some fixed ratio by mass. Examples of molecules could be H2O, water, could be CO2 for carbon dioxide, it could be C12H22O11, which is table sugar. Molecules have discrete shapes and bond angles, and we'll learn about how we can predict what those shapes and bond angles are later in the chapter. The forces that hold molecules together are covalent bonds. Covalent bonds are the bonds between 2 nonmetals where electrons are being shared. Shared is the key word with a covalent bond. Let's imagine what happens as 2 hydrogen atoms, each with 1 electron, are going to come together in order to form a covalent bond and make the molecule H2, which we know as hydrogen gas. As the 2 atoms approach each other, the electron of each atom will begin to feel the attraction of both nuclei. This will cause the electron density around each nucleus to shift towards the region between the 2 atoms. Therefore, as the distance between the nuclei decrease, there's going to be an increase in the probability of finding either of the electrons near either nucleus. The hydrogen molecule is formed when each of the hydrogen atoms in the H2 molecule acquires a share of the 2 electrons. So the region between these 2 nuclei, if the spheres here represent our positive nuclei, this region between them would represent our covalent bond and the sharing of our electrons. Each covalent bond is made up of 2 electrons being shared. 2 electrons represents 1 bond. We can build upon our Lewis symbols in order to draw Lewis structures for our molecules. We're going to want to share our electrons so that each of our atoms can have an outer octet of 8 electrons. For example, how could we draw the covalent bonding in Cl2? If we remember what each of our Lewis symbols for chlorine were, chlorine was in group 7A. Therefore, it had 7 valence electrons. Each Lewis symbol looked like this. We had a pair on 3 sides and 1 lone electron on the other, adding up to our total of 7. And our other chlorine atom would look identical. So if we're going to form a bond between each of our chlorine atoms, The ones that are going to pair up are the single ones on each side. These two would come together and be shared. The sharing of those electrons is one covalent bond. We connect the single dots in order to represent the bond. The electrons on the outside that are paired together are referred to as lone pairs. We never have single lone electrons. We always will have the electron paired up with another one, so they'll come to us as a group of two. In this example, each chlorine atom only needed one more electron in order to complete its octet. So when we count the electrons around them now that the bond has been formed, we add up both of them from the bond because they both think they own it. So this chlorine atom has 1, 2, 3, 4, 5, 6, 7, 8. This chlorine believes it owns all 8 electrons there, even though it's sharing 2 of them. And our outer chlorine atom would think the same thing. 1, 2, 3, 4, 5, 6, 7, 8. So they both believe they have 8 electrons, and therefore they're obeying the octet rule. Before we can draw Lewis structures, the last concept we need to understand is electronegativity. Sometimes electronegativity is abbreviated with EN. Electronegativity is the ability of an atom in a covalent bond to pull electrons towards itself. It essentially tells you where the electrons like to hang out in a polar covalent bond. So if we have two atoms that have different electronegativities, their abilities to pull electrons towards themselves will be different, and therefore one will be more electron greedy than the other. By using the concept of electronegativity, we can figure out who wants the electrons more. The first scientist to develop a set of numerical values for electronegativity was Linus Pauling. The table of electronegativity tells us how electronegative an atom is, or how greedy it is to pull electrons towards itself. The higher the number, the more electronegative the atom. So looking at this, we can clearly see that fluorine has an electronegativity of 4.1. It's the highest number on the table. That means fluorine is the most electronegative element. And if we look at the polar opposite corner, francium with an electronegativity of 0.9 is the least electronegative element. The numbers in and of themselves don't mean much. We usually calculate delta ENs by taking the difference between two electronegativities. The difference tells us the degree of polarity of the bond. You have a handout for this chapter that you could print off of an electronegativity table and some ranges that tells us if a bond is ionic, polar covalent, or nonpolar based upon the differences in the electronegativity between the two atoms making up the bond. Since we don't really use the actual values on the electronegativity table very much, instead we just want to understand the trend. Electronegativity increases as we go from left to right across a period, and it decreases as we go from top to bottom within a group. So if we look at the trends as it's increasing here, it's increasing as we go from left to right across a given period. That would mean as we go from lithium to beryllium, boron, carbon, nitrogen, oxygen, fluorine, we saw fluorine had the greatest electronegativity. You might notice that the noble gases were not listed on the electronegativity table, and that's because they already have 8 valence electrons in their outer shell. Therefore, they really have no affinity to react, or really they have no reason to pull electrons towards themselves. So that's why it stopped at the halogens. As we go from bottom to top within a given family, the electronegativity is also increasing. Just by knowing this general trend, we can make predictions about what type of bond will form between different atoms. Elements that are located in the same region of the periodic table, for example, nonmetals, will have similar electronegativities, which means that if they form bonds with one another, the electronegativity difference will be small, and the bonds will be more covalent than ionic. On the other hand, if elements from widely different regions of the table combine, there will be a large delta En, or a large difference in electronegativity when the bonds form, and those bonds will be predominantly ionic. Lewis structures can be used to describe the structure of various molecules. We can make reasonably accurate predictions about the shape of the molecules and their bond angles based upon their Lewis structures. Let's go through the rules for drawing Lewis structures. Number 1, add up the total number of valence electrons. The valence electrons can be found by looking at the group number for a particular element. If we have a polyatomic ion, we would add 1 for each negative charge on an anion, and we would subtract 1 for each positive charge on a cation. Determine the central atom. The central atom is usually the least electronegative atom. Often the first element in a chemical formula is the central atom, or it could be the atom that there is less thereof in the formula. Hydrogen can never be a central atom. Hydrogen only forms one bond. Arrange the other atoms around the central atom and draw a skeleton structure by connecting with single bonds. Every time you draw a line that represents a single bond, which uses up 2 electrons from the total valence electron count. Number 4, complete the octets for the outer atoms. Outer atoms means everything that's not the central atom. We want to complete those outer octets first. 5, place leftover electrons as lone pairs on the central atom. If we get done completing the outer octets and we still have electrons left over, those go as lone pairs on the central atom. Only create double or triple bonds if necessary to complete an octet on a central atom. This would be a situation where we get done completing the outer octets and our central atom still has an incomplete octet. Then we'll have to consider creating multiple bonds in order to give everybody an octet. Draw Lewis structures for the following molecules: CF4, NH3, and CO2. So the first step is to figure out our total number of valence electrons. So our valence electrons we can calculate by looking at the group number and multiplying by the number of atoms present. So the group number for carbon is 4, so carbon has 4 valence electrons. Fluorine is in group 7A, so it has 7 valence electrons, and there's 4 fluorines in this molecule, so we're going to have 7 times 4. So our total valence electrons is going to be 32. For NH3, our valence electrons will be 5 for nitrogen because it's in group 5A. Hydrogen has 1 valence electron and we have 3 hydrogens, so our total will be 8 valence electrons that we have to place. And for carbon dioxide, our valence electrons will be 4 for carbon plus 6 for oxygen times 2 oxygens. We'll have 16 valence electrons. Now that we know how many electrons we have to place, we need to draw a skeleton. Let's start with CH4. The least electronegative atom is carbon. Recall our trend for electronegativity. It increases as we go up a group, and it increases as we go left to right across a period. So carbon's going to be our central atom, and it's going to be surrounded by 4 fluorine atoms. We know that they have to be connected to carbon with at least a single bond. So the first thing we can do to make our skeleton is connect our fluorines to our central atom to make single bonds. In doing that, we used up 8 electrons. Therefore, if we take our 32 minus 8, we're going to have 24 electrons that we still have to place. The next step is to complete the octets on the outer atoms. We're going to do that by using lone pairs. So on one of our fluorines, the fluorine right now thinks that it has 2 electrons from the bond, and it wants to have 8. So we'll have 2, 4, 6, 8. It has 3 lone pairs, and it'll be the same on all the fluorines. They all think they have 2 from the single bond. So 2, 4, 6, and then 8 from the bond. 2, 4, 6, 8 from the bond. 2, 4, 6, and then 8 from the single bond. So everybody now has a complete octet. In completing the outer octets on our fluorine atoms, we used up the rest of our 24 electrons. Therefore, we have 0 electrons left. This is what we want. We want to use all of our valence electrons when building our Lewis structures. So then we would check and make sure everybody has a complete octet, and everybody does. And so therefore, since the octet rule is obeyed, the Lewis structure is complete. Let's do NH3. In this example, we have nitrogen listed first and then hydrogen. And you might be wondering who our central atom is. And if you recall, there's a rule that hydrogen can never be a central atom. So even though nitrogen is a little bit more electronegative than hydrogen, nitrogen is going to have to be our central atom. So we'll write nitrogen and we'll surround it by our 3 hydrogen atoms. And the first step is to draw our skeleton and connect with single bonds. So we have to use 2 electrons here to make a single bond, 2 electrons here, and 2 electrons here. So in making our skeleton, we used 6 electrons. So 8 minus 6, we have 2 electrons left. Any leftover electrons get placed as lone pairs on the central atom. So those are going to go on our nitrogen. Hydrogen follows something known as the duet rule, where it only needs 2 electrons to be happy because the only orbital hydrogen has is a 1s. Therefore, it can only fit 2 electrons in that 1s orbital. So hydrogen is kind of the exception to the octet rule. Now we've used up our last 2 electrons as a lone pair on our nitrogen, so we have 0 electrons left, and everybody is either following the octet rule or the duet rule. So this would be our Lewis structure for NH3, which is ammonia. And looking at CO2, which is carbon dioxide, in this case, carbon is going to be our first atom listed. It's also our less electronegative atom, so it's going to be in the center. So if we put carbon first, surrounded by our 2 oxygens, and we have 16 electrons to place, we're going to start by placing a single bond in between each carbon and oxygen. Doing that uses up 4 electrons. Therefore, we have 12 electrons to place still. Next, we move and we complete the outer octets on our oxygens. So they think they have 2 electrons from the single bond. So 4, 6, 8, and then doing the same for our other one. 4, 6, 8. In completing the outer octets on oxygen, we used all 12 of our remaining electrons. Therefore, now we have 0 electrons left. But if we check our Lewis structure to make sure everyone has an octet, we will notice that while both of our outer oxygens have octets, our central carbon atom does not have an octet currently. When we run into a situation like this, we have to make multiple bonds in order to give everyone an octet. If we take one lone pair from this oxygen and we were to move it in between carbon and oxygen, and if we were to take one lone pair from this oxygen and move it in between carbon and oxygen, let's redraw our structure. We would have carbon, oxygen, oxygen, and put back our single bonds. We'd be left with 2 lone pairs on each of our oxygens, and now we have a bond here and a bond here. Therefore, we have a double bond in between each of our carbon and oxygens. Now, if we were to see if everyone has a complete octet, oxygen thinks that it has 2, 4, 6, 8 electrons. So there's 4 electrons contained within this double bond. So therefore, it believes it has an octet. Carbon thinks that it has 4 electrons from the left side and 4 electrons from the right side. Therefore, carbon thinks it has an octet. And the right oxygen has 2, 4, and then 4 electrons from the double bond. So now everyone believes they have an octet of electrons. So everybody's happy. So if I redraw our structure so we can see it, we would have this for carbon dioxide. So we only make multiple bonds if we run out of electrons at the end and not everybody has an octet. Next, let's draw Lewis structures for ions. Notice we have NO3-, which is the nitrate ion, and NO2-, which is the nitrite ion. Let's calculate the total number of valence electrons first. Nitrogen is in group 5A, so it'll bring 5 electrons to the dance. Oxygen is in group 6A, so it brings 6. We have 3 oxygens, plus we're going to add 1 for the negative charge on the ion. So since it's a negative charge, we add 1 electron. And our total number of electrons for nitrite will be 24. And for nitrite, if we calculate our valence electrons, we're going to have 5 for nitrogen, plus 6 for each oxygen, times 2, plus 1 for the negative charge on the nitrite ion. Our total electrons will be 18. We're going to start by drawing our skeleton structures. So nitrogen surrounded by 3 oxygens. Next up is to connect with single bonds. So 2, 4, 6. So we've used 6 electrons when we made our single bonds. So 24 minus 6, we're left with 18 electrons to finish placing. Next, complete the octets on the outer atoms. So the outer oxygens, they all believe they have 2. So 4, 6, 8, 4, 6, 8, 4, 6, 8. When we completed the outer octets, that finished using our 18 electrons. So now we have 0 electrons left. And everybody has a complete octet except our nitrogen atom. Right now our nitrogen atom only has 6 electrons around it if we count 2 in each single bond. So just like we saw before, we're going to have to take one of the lone pairs, we can pick any one, and we're going to have to move it over to create a double bond. So our nitrogen thinks that it has a complete octet. So if we redraw our structure, we're going to have single bond, single bond, single bond, and then one of our lone pairs got moved over to make a double bond in between our oxygen and our nitrogen. And then we have 3 lone pairs on 2 of the outer oxygens and 2 lone pairs on the oxygen that we moved one to make a double bond. Now nitrogen thinks that it has a complete octet because it has 2 electrons right here, 2 electrons here, so that's 4, and then 4 electrons in the double bond, so that's a total of 8. Whenever we draw the Lewis structure for an ion, we also put brackets around the total structure, and we put the charge on the outside of the brackets. So since it was nitrate, it has a -1 charge. This is because once we add that extra 1 electron in, it's just like any of the others. And so looking at the structure, we might not know that it's an ion. This helps when looking at just the Lewis structure to realize that the thing has an overall -1 charge. Let's draw the structure for NO2-. So we have nitrogen surrounded by 2 oxygens. We want to connect with single bonds. So 2, 4 electrons. So 18 minus 4. We'll have 14 electrons left over. Complete the outer octets. So oxygen thinks it has 2, 4, 6, 8, 2, 4, 6, 8. We've completed their octets, and in doing so, we've used up 12 electrons. So 14 minus 12, 2. So now we have 2 electrons left over. Any remaining electrons get placed as lone pairs on the central atom. So we're going to go back to our nitrogen and place those lone electrons as a lone pair there. Now if we check and make sure everyone has an octet, we can see each of our oxygens have 8 electrons, but our nitrogen currently only has 6. 2 from each single bond, so that's 4, and then 2 more from the lone pair on it. So we have to move one of our lone pairs on oxygen over and create a double bond. So if we redraw our structure, we're going to have lone pair on nitrogen, complete octet on all of our oxygens. Our right oxygen will have 3 lone pairs, our left oxygen will have 2, single bond, and then a double bond that we just created between nitrogen and oxygen. Lastly, because it's an ion, we would put brackets around it and then a -1 on the outside to show the charge. And if we check our nitrogen now, we have 2, 4, and then 4 more from our double bond. So now nitrogen has a complete octet, and as well as our oxygens still do. So everyone has completed their octet rule. Just as we saw with hydrogen, there are a few exceptions to the octet rule. Some compounds form what's known as incomplete octets. Incomplete octets will be formed by atoms that have less than 8 electrons around that central atom. There are some atoms that can have expanded octets. This is where they will be allowed to have more than 8 electrons around the central atom. Atoms that often form incomplete octets are hydrogen, beryllium, and boron. We said that hydrogen follows what's known as the duet rule, where it only forms one bond and only needs 2 electrons to be happy. Beryllium only forms 2 bonds, therefore it's happy with 4 electrons. So beryllium would form compounds like this. And boron only forms 3 bonds, so it's happy when it has 6 electrons around it. Boron would form compounds like this. These are the only incomplete octets that we will see. If we see beryllium, boron, or hydrogen, we have to remember that we're not going to follow the octet rule for those atoms. So if we draw the Lewis structure for BH3 and we calculate our valence electrons first, boron is in group 3A, so it's going to have 3 valence electrons. Hydrogen's in group 1A, so it has 1, and we have 3 hydrogens, so 1 times 3. Our total valence electron count will be 6. Our boron is our least electronegative atom. It's actually less electronegative than hydrogen, so it's going to go in the center. And then for our skeleton, we surround our boron with 3 hydrogens. And then we only have 6 electrons to place. So when we connect with single bonds, we use 2 electrons here, 2 electrons here, and 2 electrons here. So we've used up all 6 electrons just making our single bonds. This is the correct structure for BH3. Boron has that incomplete octet. Atoms that are in the 3rd period or lower on the periodic table, so meaning the 3rd period, the 4th period, the 5th period, can accommodate extra electrons around them and can have expanded octets. This is because once we're in the 3rd period and lower, there are d orbitals available. In the 3rd energy level, what subshells do we have? We have S, P, and D. That corresponds to an L of 0, 1, and 2. And even if there are no electrons in the d subshell, just having those 5 d orbitals available can allow for extra electrons to be accommodated around the central atom. So we only see expanded octets for atoms that are in the 3rd period or lower, never in the 2nd period. Let's consider the orbital diagram and electron configuration for phosphorus. If we write the shorthand notation for phosphorus, Z is equal to 15, and our preceding noble gas before phosphorus is neon. And so we're going to have neon brackets brackets, 3s2, 3p3. And so when we write out our orbital diagram, we normally would just write the 3s, and then we would show our 3p orbitals, and all of them would be half fill. What we don't normally write is those empty 5 3d orbitals, but they are there. Once we hit the 3rd main energy level, where n equals 3, there are 3d orbitals whether an atom is using them or not. So since phosphorus is in the 3rd period of the periodic table, it has those d orbitals that it can use to hold extra electrons if necessary. Therefore, this element could have an expanded octet. Draw the Lewis structure for PCl5, so phosphorus pentachloride. Our valence electrons for phosphorus is in group 5A, so it'll have 5. Chlorine's in 7A, so it'll have 7, times 5 for each chlorine. So our total number of electrons that we have to place will be 40 electrons. Phosphorus is our least electronegative element that goes in the middle, and it'll be surrounded by 5 chlorine atoms. And notice when we draw our skeleton structure, just connecting each of our chlorine atoms with single bonds, since each single bond is 2 electrons, we've used up already 10 electrons. So we have 30 electrons that remain, and our phosphorus has more than 8 electrons around it. It has 10. That's okay because phosphorus can have an expanded octet due to it having those d orbitals available to have extra electrons around it. So when we go to place our remaining 30 electrons, we just need to complete the octets on our outer chlorine atoms. So we're going to have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30. So completing our outer octets used up the remaining 30 electrons, so we have 0 electrons left to place, and this would be our correct Lewis structure for phosphorus pentachloride. Let's consider the bonding in the following 3 molecules, HCl, O2, and N2. If we were to draw the Lewis structures for each of these compounds, we would see HCl looks like this. O2, or oxygen, would have a double bond between each oxygen atom and look like this. And nitrogen, N2, would have a triple bond between each nitrogen atom with a lone pair on the outside and look like this. We can describe the bonding in each of these by considering the difference between a single bond, a double bond, and a triple bond. Every covalent bond is characterized by 2 quantities. The bond length, which is the average distance between the nuclei held together by the bond, and the bond energy, which is sometimes also called the bond strength. This is the amount of energy needed to separate the 2 atoms to produce neutral atoms again. When a new bond is formed, an equivalent amount of energy is released as the potential energies of the atoms are lowered. Therefore, bond energy can also be thought of as the amount of energy released when a bond is made. If we think back to our 3 examples, we had a single bond between hydrogen and chlorine, we had a double bond between 2 oxygen atoms, and we had a triple bond between 2 nitrogen atoms. A single bond represents 2 electrons, a double bond represents 4 electrons, and a triple bond represents 6 electrons. The pattern between bond length and bond strength can be seen when looking at these examples. The pattern for bond length is that a single bond is longer than a double bond, which is longer than a triple bond. So our triple bond will be our shortest in length, and our single bond will be our longest bond. This is due to the nuclei in one atom being highly attracted to the electrons within the bond. In a triple bond, since there's 6 electrons, the nuclei of a nitrogen atom is going to be very tightly pulled in because those 6 electrons are going to have interactions with that nucleus. The exact opposite trend is seen for our bond strength. Our triple bond is going to be our strongest bond, with 6 electrons holding together that triple bond, with the double bond being a little bit weaker than the triple bond, and then the single bond being the weakest bond. This is the amount of energy that will be required to break this bond, or we can think about it as the amount of energy released when the bond forms. There are 2 types of covalent bonds that we can consider. The first is called a nonpolar covalent bond. In a nonpolar bond, electrons are equally shared. Recall our trend for electronegativity. Increases as we go from bottom to top of a family and left to right across a period. In the example of H2, we have hydrogen bonded to another hydrogen. If we were to calculate the delta En, or the difference in electronegativity between 2 hydrogen atoms, we would come up with 0, because both atoms are identical. This means that the electrons contained within a hydrogen-hydrogen bond are spaced perfectly in the center between them. There's no overriding pull that's winning because they both have the same electronegativity, meaning they both have the same want to pull at those electrons within the covalent bond. This leads to the overall compound being nonpolar. Typically, when we have atoms that are bonded together that have an electronegativity of less than 0.5, they can be considered overall nonpolar covalent molecules. On the other hand, we can have a polar covalent bond, or just a polar bond, since the covalent is understood. If we have a covalent bond, but those electrons are not equally shared, this leads to a molecule that develops partial charges due to the unequal sharing of those electrons. If we consider a bond between hydrogen and chlorine, we have a hydrogen atom bonded to our chlorine atom. They are not going to have the same electronegativity. Chlorine is more electronegative than hydrogen. That means that chlorine's ability in a covalent bond to pull electrons towards itself is much greater. So we know in the covalent bond that represents 2 electrons, but now they're not going to be right in the middle anymore. The 2 electrons are going to be hanging out way more by the chlorine atom than they are going to be by the hydrogen atom because of chlorine's high electronegativity. This leads to our molecule developing partial charges. The chlorine has extra electron density surrounding it, therefore we say it develops a partial negative charge. That symbol is the Greek lowercase letter delta, and then the negative means, the Greek delta means partial, and so when we put a negative by it, it means partially negative. Because those electrons are being pulled towards the chlorine and away from the hydrogen also develops a partial charge, but it develops a partial positive charge due to its lack of electron density in the bond. The other way that we can represent electron density is not just with partial charges, but we can also use something known as a dipole arrow. A dipole arrow points towards the more electronegative atom, and there's a cross at the end where the more electropositive atom is, which is hydrogen in this case. So whether you use partial charges by using lowercase Greek delta to show, or you like to use a dipole arrow, both are equivalent ways to represent your polar covalent bond. Bond polarity can be seen as a spectrum. If we consider the bonding in hydrogen, hydrogen fluoride, and sodium chloride, we can compare the polarity of the 3. In hydrogen, we have 2 hydrogen atoms bonded together that are identical. Therefore, this was called a nonpolar covalent bond. Some sources use the word pure covalent bond. This is going to be the most nonpolar that we can see when we have 2 atoms that are the same bonded together, leading to a difference in electronegativity of 0. In the middle, we have a polar covalent bond, or just covalent bond for short, and this is slightly polar. This is where we have 2 nonmetals bonded together, but they have a difference in electronegativity. That difference in electronegativity brings on partial charges. So therefore, in this example, fluorine is more electronegative than hydrogen, so the electrons within the bond are going to be more closer to fluorine. That'll make fluorine develop a partial negative charge, and hydrogen, because the electrons are pulled away, will develop a partial positive charge. Polar covalent bonds are always going to have one atom that's more partially negative and one that is more partially positive. In an ionic bond, this is the most polar type of bond we can have. Ionic bonds don't have partial charges, but they have full charges. Recall that ionic bonds are made up of a metal cation and a nonmetal anion. The metal cation is formed when a metal gives up one or more of its valence electrons, and a nonmetal anion is formed when a nonmetal gains one or more valence electrons to complete its octet. The charges are full charges, so we don't use that lowercase delta anymore. Sodium has a full +1 charge, and chlorine has a full -1 charge. This is why ionic bonds are the most polar, since they have these full charges. We can also recognize an ionic bond due to having a metal on the left-hand side of the periodic table with a nonmetal on the right-hand side of the periodic table. Which of the following species has the least polar bond? There's two ways that we can go about answering this question. One is by using an electronegativity table to actually calculate the delta En between the two different atoms. The other way is to just use our general trend of electronegativity to make some assumptions. Let's try both ways. Delta En for H and F. Fluorine is 4.1 minus hydrogen, which is 2.1. The difference in electronegativity for a hydrogen-fluorine bond will be 2.0. For hydrogen chloride, delta En, chlorine is going to be an electronegativity of 2.9 minus 2.1 for hydrogen. Therefore, our delta En will be 0.08 for a hydrogen chlorine bond. For HBr, our delta En, bromine is 2.8 and hydrogen is 2.1. So if we take the difference between those two, our delta En will be 0.7. We can rank the polarity based upon the delta En. So the largest delta En will equal the most polar. So hydrogen fluorine would be number 1, and then hydrogen chlorine would be number 2, and hydrogen bromine bond would be number 3. So from the difference in electronegativity, we can see that HBr is our least polar bond. But if we didn't have a table of electronegativity in front of us, and we just had to use what we know about the trends from the periodic table, this is our trend in electronegativity. It's increasing in this direction and increasing in this direction. So if we are looking at 3 different elements that are within the same family, in this case the halogens, we can look at their location. We have fluorine, and then below fluorine we have chlorine, and then below chlorine we have bromine. And since we're comparing them all to a bond with hydrogen, we can make some assumptions here. Fluorine is the highest within that family, therefore it's the most electronegative. Bromine is the lowest within that family, therefore it's the least electronegative, at least in our groupings here. And chlorine is going to be in the middle. Since we could determine that bromine is the least electronegative within our group of the 3, a hydrogen-bromine bond must also be the least polar as well. So even if we didn't know the actual values off of an electronegativity table, we could still come to the same conclusion, that HBr must be the least polar bond.